All right, so let's cover some data and statistics. We're going to do lessons 9 and 10. We're going to start by analyzing data in a table, using data to calculate probability, and answer questions that involve measure of center for data set, mean, median, mode, as well as draw some conclusions about these measures. So we're given a histogram here that summarizes the distribution of time worked in hours by 40 employees in a week for a landscaping company. In the histogram, the first bar represents workers who works 10 hours, more than 10 hours, or at least 10 hours but less than 20, and the second one represents at least 20 hours but less than 30, and so on. Which of the following could be the median and mean amount of the time worked for the 40 employees. So the first thing we want to do is look at median, okay? The thing to remember with histograms is we're losing a lot of data within each of these bars. I know that 6 employees work between 10 and 20 hours a week, but I don't know exactly how many hours. They could have all worked 19, they could have all worked 10, or somewhere in between. I don't know what those exact values are, and the same is for each bar. But what I do know is that most of my employees worked somewhere between 10 and 40 hours within that week, okay? And that's pretty standard because over 40 is considered overtime. And so the bulk of my employees are within that 20 to 30 range, and so what we can do is look at find the median. It's a good bet that our median is going to be somewhere between 20 and 30, but let's verify. When we're looking at median, we can find the median number or median place using a simple formula where it's n plus 1 divided by 2, n being the number of values in our data set. Since we have 40 employees, n is going to be 40. We add 1, divide by 2, we get 20.5. So that means our median numbers are actually going to be the 20th and the 21st employee in the data set. Now, if we just start on the left-hand side and count till we get to the 20th employee, 0, 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So our 20th and 21st employee are both within the 20 to 30 range. So we can go ahead and eliminate answer option D because it has a median that's too high. The second thing that we need to look at is kind of twofold. Within the mean of our options, okay, a couple things that we need to identify is that our data is what we call skewed to the right. Normally distributed data, we're going to have a nice bell curve where most of our data is somewhere in the middle here. But if I've got this longer tail on the right-hand side, as we see that we have here, because we have these outliers, some people that are working over 50, 60 hours a week, we're skewing our data to the right. Skew right. And when we skew to the right, what we're doing is we're going to be pulling the mean further to the right. The median will also be pulled to the right as well, but not as significantly as the mean value is. And so our mean is going to end up being greater than our median. And by looking at this skewing, I would say that it's probably a safe bet that our median is going to be probably moved into the next column here. And so that's going to leave me with answer option C. I'm also going to look at A and B and realize that, okay, well, these aren't very far from our median. The answer option B, the median isn't even, the mean isn't pulled to the right of the median. It's actually less. So our mean is not going to be less than our median in this data set. Our mean is going to be greater. And a mean of 23 is not that much bigger than 22, which is why I would reason that C is going to be our best bet. Now here we're given a two-way table on the efficacy of a security system. Based on the data provided from the other security systems, he's able to estimate the efficacy of a new one that he's installing. According to the estimates that the alarm sounds for a customer, what is the probability that the customer did not attempt to shoplift? So there's two important things to look at with the two-way table. So if the alarm sounds for a customer, what is the probability that the customer did not attempt to shoplift? Well, since we're looking at if the alarm sounds, the only thing that I really care about is the instances in which the alarm sounds, which is what this column represents. The alarm went off. Those are the 56 times that the alarm went off. So when we're dealing with two-way tables, you need to identify and figure out what situation are you focusing on and use that to draw your probability. So if the alarm sounds, what's the probability that the customer did not attempt to shoplift? And so we need to look and see, customer does not attempt to shoplift, that's 35. So 35 times out of the 56 times that the alarm sounded will give us the probability that a customer was not attempting to shoplift, okay? So just some quick glances, we can see that 35 is close to 56. We're probably going to, or I'm sorry, close to half of 56. So we're probably going to get something that's around 50%. If we do the actual division, we see that we get 0.625, but again, we need to remember to turn that into a percent, which is 62.5%, which gives our answer option D. But again, we don't even need to do that division. Say we end up with something on a calculator or non-calculator portion. We're looking at, again, realizing that that's close to half. Well, 0.3% is way too low. 0.35% is way too low. 0.56% is way too low. These are all less than 1%. All of these values were found by using 10,000 as the denominator instead of the 56. And that's the trick with the two-way table, is making sure you have the appropriate denominator. So here in this two-way table, we want to finish filling it in. Margot classified her favorite paintings hanging in a museum by both size and dominant color. The results are in the table. Margot found that 1/4 of her favorite large paintings were blue. So we're focusing on large paintings, and she found that 1/4 of them are blue. 1/4 of her large paintings were blue. Well, that ended up being 5. So if that's our ratio, we can set up a quick proportion and say one blue painting for every 4 large paintings. And if we know that 5 blue paintings out of how many large paintings, we now have our proportion that we can solve, and we get x equals 20. And so that fills in this column with the total number of large paintings. And then from there we can work backwards and we can fill in red. We go up here and we say, okay, well, I have a total of 20 large paintings. 5 of them are blue. If I subtract that 5, I end up with the other 15 large paintings being red. And then from there I can keep going and say, oh, well, now I have this information. If I have 15 large red paintings and 4 small red paintings, I know that I have 19 red paintings in total. And if I wanted to, I could keep going and fill in the rest of these values here, but I don't need to, because if we finish reading the question, how many of Margot's favorite paintings have red as the dominant color? Well, we just answered that. It's 19. So just a review on probability and statistics. Probability is the measure of how likely an event is. When calculating the probability of an event, use the following formula, where the numerator is the number of favorable or desired outcomes, and we'll put that over the number of possible outcomes. And then we have our measures of center, mean, median, and mode, and then our measures of spread being range and standard deviation. So, looking at this one, we have the table shown partially reports the number of civil aircraft produced in the United States during the course of 5 months. If there was a mean of 325 civil aircraft produced during that time, how many were produced during month B? And so what we need to do is we need to figure out, okay, well, how do I find mean? Well, we calculate mean by taking the sum of all of our data values and dividing it by the number of data values we have. So we'll take the number in month A plus the number in month B, which we don't know, plus C plus D plus E. And divide that by the number of months. And that needs to equal the mean value that was given to us. So now we have an equation that we can use to solve. So we'll multiply both sides by 5. and here. So that'll cancel. We can also go ahead and combine all of these like terms. So I'm going to do that in one step. And we're going to end up getting 1,326 plus x equals 1,625. Finish by subtracting. And we get a value of 299 for x. So that is the number in 1B. Mr. Jadav raised all of his students' scores on a recent exam by 10 points. What effect did this have on the mean and the median of the scores? Okay. Well, if we take all of the data points, if I have 5 tests, I'm going to have some median value in the middle. Well, if I increase all of those by 10, that means all of those data values are going up 10 more. That means whatever that median value is also going to increase by 10. So I know that the median is going to go up by 10. So let's remove median remained the same. And this one that also says median remained the same. So now we need to determine if the mean is also going to increase. Well, think about it. The whole point of increasing the scores is so that the average goes up. If I have bigger numbers here, when I'm finding my mean, that means I'm going to have a larger total that's going to be divided by 5. So the mean will also increase. So both the mean and the median are going to increase by 10 points. A store has 5 different lengths of extension cord for sale, as shown in the table, with the range of lengths of the 5 cords is 7 feet. What is the greatest possible value of x? Well, we have 2 possibilities. X could be either the largest or the smallest cord. We don't know. But if we're looking for the greatest possible value of x, it's safe to say that we want x to be our largest number to figure out what the largest value would be. Well, in order to find range, we take the largest value and we subtract the smallest value. Well, in this case, I know that the range is 7 feet, and my largest value, I want it to be x, so that way I have the biggest possible number. So then I have to look and see, well, what's the smallest value that I have left in the list? That's going to be 6 feet. And so then we just need to solve for x. Add 6 to both sides. 13 is the largest value for x. If we wanted to flip it around and just say, okay, well, what if x was our smallest value? Well, we would just switch our equation and we would say, okay, well, my largest value is 11. My smallest value is x. Let's go ahead and solve for x. Well, subtract 11. We get -4. So x would equal 4 if x was the smallest length. Now, when we're interpreting data, if you're asked to compare standard deviation, you should first approximate the mean. Just get a real quick estimate and determine which data set has values that are more closely clustered around the mean. That data set will have smaller standard deviation. When a confidence interval is provided, you should determine the value for which the interval applies. Confidence intervals concern the average value of a population and do not apply to the individuals. You'll never be asked to calculate a standard deviation, a margin of error, or a confidence interval, but you will be expected to understand what these concepts mean and interpret them in the context. So here we have 2 classes with quiz scores, Class A and Class B. We want to figure out which one of these is going to have a smaller standard deviation. Well, standard deviation tells how closely scores are clustered together. So the closer data is to the mean, then we're going to have a smaller standard deviation. A smaller standard deviation, the closer all the data is to the mean. So if we look quickly at Class A, we see that most of our data is somewhere in here. So our mean is probably located about 3 point something. And then in our class B, we've got a pretty even spread, so our mean is going to be right here in the middle. Well, if we just kind of take a quick look at the data points in each of those sets, we can see that if my mean is here in the middle, between 3 and 4, I have a lot of data points clustered really closely around that estimate of my mean. So everything is clustered closely together. So that means I'm going to have a fairly small standard deviation. But here, all of my data points are evenly spread out. If they're evenly spread out, that's going to end up being a larger standard deviation when they're all evenly spread out. So here we can see that since there's more clustering within Class A, the standard deviation for the quiz scores in Class A is going to be smaller. We're looking for more clustering, smaller standard deviation. Now let's finish up with Lesson 10. Let's look at some characteristics of populations and investigate relationships between variables to get conclusions. The quality control researcher in an electronics company is testing the life of a company's batteries. They find that 100 batteries selected at random from the daily output, that the life of the batteries is a mean of 342 pictures with a margin of error of 18. Which of the following is the most appropriate conclusion based on the data? So what this margin of error says is, hey, our mean is 342, but we may be off by a little bit, plus or minus 18. So that means if we add or subtract 18, that's where they're getting these numbers of 324 to 360. So they have some confidence interval of maybe 95% or 98%, and they're saying that the mean of these batteries is going to be somewhere within this range. So all the batteries produced by the company that day have a life between 324 and 360. Well, the big issue here is it says all the batteries. We just took a sample. We don't know for sure if all the batteries will have a life between that. We'll be confident that most of them will, but we can't say that all of them will. All the batteries ever produced by the company have that life expectancy. Again, all. We can't make that assumption. And also, it's ever produced. We only tested one day. We'd have to test over many, many days in order, or every single day, to make a better determination. Is it plausible that the mean life produced by the company that day is between? Yeah, it's definitely plausible that the batteries produced that day could be between those two numbers. Is it plausible the mean life of all the batteries ever produced? No, not ever. So we're going to go with answer C. Community Center offers a Spanish course. This year, all students in the course were offered an additional audio lesson they could take at home. The students who took these additional audio lessons did better in the course than students who didn't take the audio lesson. Based on these results, which of the following is an appropriate conclusion? Taking audio lessons will cause an improvement of any student who takes any foreign language course. Well, this is only talking about a Spanish class, so we can't assume that it will work for every foreign language. Taking additional audio lessons will cause an improvement for any student who takes a Spanish course. Okay, well, I mean, and we're getting closer at Spanish, but this was all done at a specific community center. So different Spanish teachers may be better. Who knows whether an audio lesson would help or not? We don't know. Taking additional audio lessons was the cause of the improvement for the students at the community center who took the Spanish course. Okay, that looks a lot better. We're specific with community center and that Spanish course. Problem is, the additional audio lessons were optional and voluntary. If it's voluntary and not a random sample, we cannot make any conclusions about that data set. We're going to have to go to D. While C is very, very close, the problem is that they didn't assign it randomly. If they had said instead, half the students, half the students were given audio tests, were picked at random, then yeah, we could probably make a determination and choose C. But that's not the case. They voluntarily had the option to take it. If they did, those students did better. But who knows if it was the audio tape? We're making a causational assumption on something that's just a correlation. We cannot make any conclusion. A researcher collecting information about a bunch of physical therapists find that their salary was between those two numbers with a 95% confidence interval. So with 95% accuracy, 95% confidence, we know that these physical therapists will make between $22.76 and $59.24 hourly wage. Which of the following could represent the median hourly wage based on the same sample for physical therapists with a 90% confidence level? So, when we decrease the confidence, okay, what we're doing is we're actually tightening up that interval, okay? So we can be closer to the true median with less of a spread in that range. If we were to increase the confidence interval, then we would have to widen that range. So let's kind of look at some of these different values here. If I do $17 to $65, I'm just going to do some estimates. $17 to $65. This would be a larger confidence level. Okay, so that's not going to work. We want a smaller confidence level. We want only 90%. Look at the next one. We've got 20 to 53. So 20 is right here, and 53 is right about here. Okay, well, that may be about the same size, but it's also just shifted to the left. So we didn't really change the confidence interval, we changed the median. So that shifted the median. Okay, that gave us a larger confidence. Next one, we're looking at 21 to 56. Okay, a little bit better, but not quite what we're looking at. Still kind of shifted everything to the left. And then we're looking at, so again, that also shifted the median here and here. So looking at this last one's got to be it. 25 to 56. That's 56 from here to there. Well, there we go. There's our smaller interval. That's what we want. That's our smaller interval. Last but not least, polling agencies surveyed 500 adults selected at random from a large city. Of those surveyed, 42 responded they support a new policy. Based on the results, which of these must be true? If of all adults in the city, 42% support the new federal policy, well, that can't be true because we don't know for sure. They'd have to ask every single adult in order to get that one. Of 500 different adults were selected at random from the same city, 42% of them would support the new policy. No, again, I don't know for sure. It might be close. It may be 40%, it may be 45%, it may be 42%. We don't know. It could be a completely different demographic. That's just too specific. If they said approximately 42, maybe. If 500 adults selected at random from a different city were surveyed, nope. Different city. Different demographic. We're going to say that none of those statements must be true. Might they be true? Yes. But none of them must